So welcome back after the coffee break, and it's a pleasure to have Ramesh Johari from Stanford. You want to tell us about A/B tests?
Okay, great. Thank you. Yeah, it's great to be here. Thanks to the organizers. I should also thank the organizers for their flexibility because up until about 2 weeks ago, I said I would talk about something else, and I'm glad that they let me switch over to this. I saw that there were a couple other talks related to experiments and A/B testing. And then I also thought this would just be work that would be potentially interesting to this audience. It's a little bit of a change of pace from most of the other types of things you'll see this week, but hopefully you'll find it interesting. So some backstory to this. This is actually not work that I did through Stanford. This is work that I did with a company called Optimizely, which runs a large A/B testing platform. I'll basically just explain to you kind of what the backdrop to the problem was. I'm going to skip this slide. I feel like most people here will probably know what A/B testing is. Basically, it's a mechanism that online platforms use to compare different versions of their websites. That's a narrow definition. These days, it's essentially used for experimentation in every sort of technology system that you can imagine. The basic idea is that you have two versions of something you want to compare. So you have visitors coming in, and you randomize them into either the control or the treatment. This is like the simplest example. You track something like a conversion rate in each group. So, for example, you might care about how effective a particular design is at convincing someone to buy a product. So you would be tracking the conversion rate from arriving to the page to actually buying the product. You could look at something like the true conversion rates, the true underlying conversion rates in each group as kind of the ground truth that you're trying to get at. And what you care about is there a difference or not between the two groups? So this is kind of classic frequentist hypothesis testing. You have a null that there's no difference, an alternative that there is a difference, and you want to essentially test that hypothesis. I think it's worth just pausing here for a second because this drives people crazy. Do I really care about whether there's just a difference or not a difference? My entire talk is going to be focused on sort of p-values for this hypothesis testing problem. But as is kind of standard in statistics, there's a duality between p-values and confidence intervals. And in practice, I would say that confidence intervals are the things that people actually care more about. But I'm not going to talk about confidence intervals during the talk at all. It would just add more notation without really any additional technical understanding. I'm happy to go through that duality if someone's interested later. Yeah, Bobby?
Question about notation. Does hypothesis 1 posit a specific non-zero value of theta?
No. It's what's called a composite. Yeah, so hypothesis 1 is just what's called a composite alternative, that the theta is something other than 0. Yeah.
What you call group?
Say again?
What is the group?
Oh, sorry. Group. By group, I mean the true variations, control or treatment. So when I say conversion rates are tracked in each group, I mean you would measure the conversion rate for all the visitors that come into the control and all the visitors that come into the treatment, and then you would compare these two. I mean, more generally, of course, the data in those is actually the entire sequence of arrivals with whether or not they converted. It turns out that for any reasonable testing purpose, all that's relevant as a sufficient statistic is the fraction that actually converted. OK, so if you go to a stats book and you look up, how should you run such an experiment? And let me preface this also by saying, I think there are lots of really interesting questions you could ask in A/B testing, and probably one of the most interesting questions is this even the problem worth solving? Okay, just in the interest of time, I'm not tackling that question. This would be largely a philosophy talk in that case. So I am going to just essentially assume that the problem I'm interested in solving is kind of this hypothesis testing problem. In a stats book, and this would be something you would learn in kind of even an undergrad stats class, what you're taught is basically that you pick your sample size in advance. And once you pick your sample size, the interface, the A/B testing platform interface, will spit out for you something called a p-value, which is essentially the probability of seeing data as extreme as what you saw, given that the null is true. Okay, so like how the p-value is measuring how likely is your data under the null. And then there's a simple decision rule, which tells you to reject the null if that p-value falls below alpha. Okay. So this is the approach that's used in virtually every A/B testing platform and dashboard, whether internal to a company or external. And one of the reasons it's used, I think it's interesting because p-values obviously have been attacked relentlessly for a variety of different reasons. I'm sure many of you are familiar with this. So I'm also not here to offer a defense of p-values. That would be a separate philosophy talk. But one of the things I do think is worth doing, though, before we completely reject them, is to ask ourselves, why were they so prominent or so useful in the first place? And I think one of the things that's worth remembering here is that this is actually a very simple decision rule. And if you're trying to design a platform that you want millions of people to be able to use without really having advanced training in statistics, then simplicity of a decision rule is kind of an appealing property. And that's probably part of the reason why this is something which actually finds its way into practice so easily, despite kind of the mess of understanding what this is actually doing underneath. And if you dig into that a bit, one of the nice things about that decision rule is when it is used correctly, then you actually get some very strong results. So you get the fact that type 1 error is bounded at level alpha, which means that the probability of a false positive is bounded at level alpha. It gives optimal power, so a true positive probability given alpha, assuming a reasonable hypothesis test was used to generate the p-value. And these two things are given to you essentially for free as a user without really having to know anything about the internals of the experiment or the analysis methodology. All that was really needed was that p-value. Okay? And so one of the nice things for a dashboard, whether, again, internal to a company or external as Optimizely is, one of the nice things about that is that many different people are going to be drawing inferences from the same data. Right? And so one of the, I think, appeals of something like a p-value or confidence intervals computed from this type of methodology in an organizational context is it allows many different people with different risk preferences to interpret the same data without having to first kind of unfilter someone else's subjective beliefs from the data. I think there are ways for organizations to intelligently build Bayesian models of the same thing, but it's definitely not very prevalent. And I think this is part of the reason that this is something which, for better or for worse, has developed a sense of being sort of objective as people use it. So I think this is an important thing. It's certainly one of the reasons I think that this coupled with the simplicity of the decision rule is one of the reasons that this is such a pervasive approach to testing. But all of that was predicated on the presumption that these things are used correctly. They are not used correctly. That's what many of the p-value hacking papers I'm sure you guys have heard about are all about. And here's an example. I just want to walk you through why they're not used correctly. It's not just that they're not used correctly. It's that we encourage you to not use them correctly. Okay? So in particular, this is an old version of what the dashboard in Optimizely would have looked like for an experiment. And the thing I actually want to point out to you here, OK, so this is a test with actually multiple variations, so different cells. This is the control, 3 different treatments. There's a number of different metrics that are being tracked, and here's your multiple hypotheses being tested. But the thing I actually want to draw your attention is in this really tiny blue font over here. And it says, how long should I run my test? Now, what that does when you click on it is it takes you over to a sample size calculator. All right? So what is that doing? It's saying, tell me how long I need to run the experiment. Now, what did I just tell you 2 slides ago? The first thing you learn in a stats book is to figure out how long you're going to run the experiment before you run the experiment. So the place that should have been was not on a results page. It should have been on a design page. Right? Why is it here? It's here because everybody asks, how much longer do I have to wait in this experiment? Right? But that is not at all what classic experimental design is set up for. You're not supposed to be recalibrating the sample size halfway through the test. Right? So in particular, what can happen is that one of the diagnostics Optimizely customers will use to determine whether the platform is doing something reasonable is to run what's called an AA test, where they just run the same version of the web page against itself. Because here you expect the platform will tell you that there's no difference. And so they run the test, and what do they find? They find, wait a second, so this is actually 1 minus the p-value. At the time, it was something called chance to beat baseline. And that crossed 95%. And if they're using a 5% p-value cutoff, then they'd be like, wait, this is significant. What's going on? So the poor customer support reps would get these calls where people are like, I just ran an AA test, and I got a significant result. I don't trust your platform, and where are the bugs in the algorithms you're using? And the truth is that just what'll happen is, if you're willing to wait, right? In that case, they didn't have to wait very long. But in general, if you're willing to wait, every AA test is eventually going to return a false positive. Okay, it's a simple consequence of the law of the iterated logarithm. If you look at the test statistic, it's guaranteed to cross any level infinitely often, any fixed level infinitely often. Okay, and so type 1 error is guaranteed. Now, that's an asymptotic result, but in fact, even on finite horizons, so here we're talking about like 10,000 visitors, with alphas of 0.1, 0.05, 0.01, you still get type 1 errors in the 30% range, okay, with that rule. You can be a little more intelligent. I won't talk about this. There's something called post-hoc power, which essentially amounts to just using an even lower alpha threshold cutoff for your p-value, and still you get very high false positive rates. So anecdotally, the impression at Optimizely is that probably just relying on those fixed horizon p-values that are shown on the dashboard and then applying this kind of continuous monitoring, people are ending up with false positive rates in the 30 to 40% range. Right? And so this is actually a fun thing for me, because when it happened, naturally, I turned to all of my expert colleagues in the stat department. And the reaction, of course, is that users are stupid. So the right thing to do is to give them a stats book and then make sure that they actually run their experiments correctly. And to be fair, it wasn't just them. It was basically this was my response too. It was like, at first, this doesn't feel like a problem, because this is a problem that the book is solving for you, right? So why are you doing it this way? And I think that kind of misses the point. The reason that people continuously monitor is actually not because they're stupid. It's because there's a significant opportunity cost to waiting. And that's just not something that was built into the experimental design structure of the platform, right? So in particular, what they really care about is that they're considering, OK, if I wait, am I likely to detect an effect here? Because if not, I would rather run another test. So there's a high opportunity cost to waiting. And they're really making this dynamic trade-off between detection and runtime on the basis of what they see. And the reason they ask, how much longer do I have to wait on this test, is because given the data I've seen, is it worth it to wait, or is it worth it to stop? Is it better to stop? So that's one thing. And the other issue I think that comes up for a platform is that that's a risk preference that's not known and not easily elicited. So the way that we're finding out about that is by how people interact with the p-values, right? Basically, if they choose to stop a test at a given time, then that's kind of an indication that they've made a relative trade-off between detection and runtime at that point. And so I guess the point I'm trying to make is that, for us, what we ended up with is that, and I guess I would say the main modeling innovation in thinking about this problem is to think of the user as an actual participant in the process. Okay, so there's the platform that's processing data. There's sort of the statistical measures that you're going to display. But then there's a user that's actually a third party that you don't completely control, that interprets the measures to take action, right? And so at some level, it's almost like a robust statistics problem where you're trying to provide some robustness with respect to this uncertainty about what the user is actually going to do. And so the goal is to deliver essentially optimal inference of the sort that I described earlier for classical p-values and confidence intervals in an environment where users continuously monitor experiments, and when the platform doesn't necessarily know the user's priorities regarding runtime and detection in advance. And I would say that this is far too grand of a claim. I should have edited this down a bit. But our work tries to address this challenge, is a better way to put it. I don't think we're going to, for reasons you'll see, it's going to be difficult to do this kind of in absolute terms. But I'll show you at least what we came up with. And one of the exciting things about this, for me at least, was that it was a chance to do some interesting sequential hypothesis testing, but actually see it deployed. So this is something which has been running in Optimizely since January of 2015. They have thousands of customers worldwide. Those of you that are surfing in the audience right now are probably at a site where Optimizely is enabled. OK, so let me just quickly run through an outline of the kinds of things I want to cover. The first thing I'm going to do, and basically as I walk through these things, what's going to be happening is we're going to go from a very general model of user and data down to a much more specific model of user and data. So the first thing I want to do is, in a very general user model, try to control type 1 error. And as I said, that's the first thing that classical p-values gave you. The next thing I want to do is I want to, now given that fact, I want to efficiently trade off power and runtime. And here we're going to have to make some assumptions about the user model with respect to which we do that. Okay? I want to tell you a little bit about exactly what the implementation meant. And here I want to talk a little bit about sort of what do we learn by looking at some of the data inside Optimizely. This I'm almost certainly not going to have time to get to, but I just wanted to point it out, which is that alongside the work here, which was really to change p-values and confidence intervals so that they were kind of sequentially valid, so they were valid under continuous monitoring, we also, once you have p-values, then many statistical methods for correcting in the presence of multiple hypothesis testing become implementable. And so one of the things we try to do is ask, when can our new p-values commute with classical multiple hypothesis testing procedures? So that, I won't talk about that much, but that's kind of, this is also something that's deployed in the commercial dashboard. OK, so let me tell you about sort of our first, oh, sorry, yeah.
Just maybe this is just a question. So do you know the hypothesis that the users are testing? Like, so can you do something like a multi-arm bandit, or that's?
Yeah, actually, so this is a great question. So let me repeat your question. It was, I think those are actually two separate questions. So one is, do I know the hypothesis the users are testing? And the other is, could I do something like a multi-arm bandit? So in terms of what the hypothesis the users are testing, the assumption that is being made is that the users are comparing each of the new variations to the baseline. Now, as I said earlier, like I could easily give an hour-long talk on all the open problems in A/B testing. And one of the biggest ones by far is that if a user has a web page and then creates 5 new variations, it's unlikely that the thing they're most interested in is a comparison of all of those against the baseline. Often they're going to care, say, for example, for best arm identification among those 5 or those 6. Or they may actually care about a bandit where it's left continuously running, and they actually want to minimize regret over time. So I would, again, I think it's a great conversation to have, probably over a drink or coffee or something. But coffee is a drink, I guess, not the kind of thing. So I was going to say is that I think it's a great conversation to have. I think for now I want to just focus in on this narrow problem where we're still maintaining the same structure. I think what I would say is that one of the interesting challenges is that people will often tell you that what they want is the best of something until they find out that the best wasn't the thing they thought was going to be best. And then they want to know why that wasn't best, and that's inference. So the problem is, retrospectively, people want inference, and prospectively, they want best arm selection. And the question is, how do you combine those two things? Neither field is really well set up to do the other well. That's actually some of the things I find interesting right now. OK. So yeah, let me talk about this first, which is how do we compute p-values that kind of give us this strong property, which is a user can look at the results whenever they want, and then if they happen to cut off the p-value at alpha at that point, they would still have valid type 1 error control. Okay? So we need to kind of make that a little bit more formal. And so this is, I guess, one of the first contributions in the paper is just this definition of what that means. So let's go back to how p-values are classically computed. What this is saying is basically that you commit in advance to little n to when you're going to look at the p-value. What I want the p-value to have at that point is that it is super uniform. Basically, that if you cut the p-value off at x and the null happened to be true, then the p-value will not fall below x more than fraction x at the time. Okay? This is exactly type 1 error control in the classical fixed horizon context. Now, here what has to happen, though, is that you need to commit to n in advance. So what I want to do is just change n to a stopping time. Okay? And so our definition is that p-values are always valid if the same thing holds, but with t being any stopping time. And what that buys you now is that the user can look at the data first and then decide when they want to stop the test. And on the basis of that, we're saying, nevertheless, we still want type 1 error control. So among other things, classical p-values won't do this because, as I told you, if you watch the p-value process as defined, let's say, from a standard t-test or something, then that's guaranteed to cross any fixed threshold. So let's say that the user stopping rule is I will stop the first time the p-value crosses a threshold. Then, of course, they're going to stop with probability 1 under the null. Okay? So our goal is to deliver p-values that actually obey this much stronger property. That under any stopping time chosen by the user, they still stop. So basically, the point is that now the user can favorably bias their choice of t based on the data that's seen, and we're trying to correct for that. Okay? It's necessarily very conservative, so you should expect that a lot is lost for doing this. And one of our goals is going to be to not lose as much as you think you might because you did this. So how do we construct these always valid p-values? And there's, for those of you with some stats background here, I'm sure that you've made the connection over to sequential testing already. So this very much feels like a sequential testing problem. And what is a sequential test? Just to fix the formalism. When I say sequential test, what I mean is it's a family of stopping times indexed by alpha, your type 1 error control, that have the property that it stops later when alpha is lower, and it bounds type 1 error. Okay, so the T alpha test terminates with probability at most alpha under the null. Right? So there's many sequential tests, and we'll talk about one in particular that we used in a second. But here's kind of the key thing for us, which is if you give me a sequential test, or this family of stopping times indexed by alpha, let me define a p-value, which is the smallest alpha, such that the alpha level test would have stopped by observation n. Okay? Then that resulting p-value process is always valid. Okay? This is actually mostly just an interchange of definitions. The proof is actually quite simple, but I'm not going to go through it so that I can get through the rest of the things I want to tell you. It's a fairly kind of easy thing to show. The nice thing about this is it means that anytime you give me a sequential test, I can produce these always valid p-values. Okay? So when in the first kind of iteration of this work in this talk that we did, we ran into a bit of trouble because this makes it look like what we're doing is converting the problem of this interface design into sequential testing. So now we've got always valid p-values. Now we just need to construct a sequential test. One of the things I don't want you to forget, though, is that a running thread throughout what we're trying to do is that the user is someone that we don't completely control. So while it's true that there's this duality between the always valid p-value processes constructed here from the sequential test, in particular, if the user stops the first time that always valid p-value drops below alpha, then the resulting stopping time is actually the sequential test, is exactly the sequential test. So because of that duality, you might think, well, OK, we can just focus on sequential testing now. The problem is that not all users are going to stop at T alpha in this case anyway. So the property that matters more to us is that we have type 1 error control for any stopping time. Right? Clearly, something should be lost if they don't follow this natural decision rule, but at least we have valid type 1 error control for any stopping time. Right? OK, so that's the first piece of the talk, which is what we wanted to do is to kind of maintain a simple dashboard that users could behave exactly the same way that they're behaving, but which now provides type 1 error control. So one of the nice things about this, actually, and one of the things I like the most, is that almost everything about the dashboard, they made UI changes more for the sake of better interface. But actually, the mechanics of the dashboard, showing p-values and confidence intervals, hasn't really changed. What we're doing is preserving something which feels natural, but just making it valid, making the process of rejections valid. And so what we're doing now on the dashboard is showing these always valid p-values computed from a particular sequential test. Yeah?
Feels a little bit like you're only looking at one experiment, but if I'm a user, I might abort the experiment because I see there's no effect.
Yeah.
And then we run the same experiment.
Yep.
And I don't see an effect. And then the 6th time I rerun, I see an effect, and I say, oh, clearly it's working.
Yeah, that's a good point. So I'll repeat that question. So basically, he said that we're only focused on one experiment here, and to some extent, there's the same problem across many experiments. I totally agree with that. So in line with the theme of many interesting questions in A/B testing, one of the things I find most interesting is that in comparison to, let's say, the design of clinical trials, where there is a feedback loop, but it's much slower and there's a lot more policy involved, in A/B testing, there's a much faster feedback loop between what you learn from one experiment and what you do next. This turns out to be not exploited nearly as much as I thought it would be. So it does suggest that there's really interesting ways to combine reinforcement learning with some of these interfaces. So I think you could think of the problem that the platform is trying to solve as sort of a reinforcement learning problem together with the user. As far as I know, nobody's doing that sort of commercially in any meaningful way, at least treating A/B testing that way. But yeah, I agree with you. I think what you said is a great point. This definitely doesn't address it. OK. So what have we done? We've controlled type 1 error. Okay. Now, as I said, that's not really the only goal. Going back to the kind of users aren't stupid point, the reason that users stop early is because they actually care about detection and runtime and the trade-off between them. So what we'd love to be able to do is say something like, we found a test and a sequence of always valid p-values that are simultaneously optimal for everybody. And of course, that's not possible. I mean, among other things, consider a user who just has a silly trade-off between detection and runtime, somebody who prefers longer tests, right, and low detection. Like, that doesn't make any sense. So what we want to do is we want to impose some structure on a user model with respect to which we can prove things. Okay? And hopefully that user model captures this trade-off in a way that's semi-meaningful. So what we thought was most interesting, the axis that we think is most interesting is this axis where a user is thinking about when should they end the test, right? So we're basically going to consider users where we choose a method of computing p-values. The user observes these p-values and wants to detect whether non-zero effects exist, so they're testing this hypothesis. And they stop the first time the p-value falls below alpha, but they're only willing to wait up to a maximum runtime of m. Okay? So our users are parameterized by these two numbers, alpha and m kind of indexes their patience. Right? So alpha is a commitment to type 1 error. M is a commitment to how long you're willing to wait. Now you can see that for any given structure of always valid p-values, this gives a decision rule the user will apply. In turn, that's going to completely determine what your power is going to look like, your ability to detect effects will look like. Okay? So our question is going to be, for these types of users, can we design tests that do a reasonably good job? That's the goal. Right? And so the question is, what always valid p-value processes deliver an efficient trade-off between power and runtime without advanced knowledge of this m? And even there, I need to be kind of careful, because I'm not going to promise you simultaneous optimality for all m. We're going to look at the large m regime and see if we can do something which is kind of first-order optimal. Okay? So for the rest of this part of the talk, I'm just going to assume a normal theta-1 model with just one stream of data, just to keep life simple. And so in particular here, I'm just getting a sequence of observations that are IID from a normal distribution with unknown mean. And I'm testing the mean of that normal. Okay? Obviously, in A/B testing, I have two streams. Some details on that you can see in the paper. This particular stuff all generalizes to single parameter exponential families. But that's, again, just more notation for the purposes of the talk. OK, so here's the test that we use. It's called the mSPRT. It's not something we invented. It's actually part of this beautiful literature on sequential tests of power 1 from the 70s. So it's a test due to Robbins and Sigmund. By the way, I gained a tremendous appreciation for Robbins, Sigmund, and Lai after working on this topic. I mean, obviously, we all know Lai and Robbins from the multi-arm bandit paper, and they've all done a lot of work on sequential testing. But there's this entire line of work on sequential tests of power 1 that really hasn't seen a lot of activity in the last 2 decades that's at least as deep as the rest of what they've done. So it's very impressive. Anyway, so here's how the test works. The notation here, this is the likelihood ratio after n observations of theta against theta naught. Okay? And what I do is I integrate that likelihood ratio against a mixture distribution. I'm deliberately not calling it a prior here, though it does have an interpretation as one. And the idea is that when the likelihood ratio of theta against theta naught is high, it means that theta is a lot more likely than theta naught. But I don't know in advance what thetas are possible. And so I integrate against this mixture distribution to kind of consider all likelihood ratios simultaneously. Right? So this is the mixture sequential probability ratio test. The sequential probability ratio test was one which just uses the likelihood ratio and waits till that hits boundaries. So we're going to use this mixture sequential probability ratio test, the mSPRT. And the way we stop, I'm going to define S alpha, the stopping time for this test, is when the likelihood ratio, this mixture likelihood ratio, crosses 1 over alpha. Okay? So you give me your alpha, I stop at the first point at which it crosses 1 over alpha. And otherwise, I continue indefinitely. Okay? This test has some nice properties. The first thing is that under the null, the likelihood ratio is a martingale. Okay? And since it's a martingale under the null, this mixture is also a martingale under the null. And so you can use standard sort of optional stopping techniques to show that the probability that this ever stops under the null is going to be bounded by alpha. Okay? And so that's the control of type 1 error under the mSPRT. Again, not our result. In addition, it has power 1, so it's guaranteed to detect any true effect eventually. Okay? Now, why is that? I'm not going to talk about this in detail either, because it's not kind of the core of my talk. But the point is pretty simple. It turns out that the mSPRT has a detection threshold, which, what was the problem with the detection threshold from a classical fixed horizon test? It wasn't that it wouldn't detect a true effect. It's that it would always cross under the null. Right? So your power is actually OK. It's that you were having, your type 1 error is way too high. It's 100%. So the mSPRT kind of strikes a delicate balancing act. It makes sure that under the null, you don't cross the detection threshold more than fraction alpha of the time. But nevertheless, it guarantees that if the null is not true, you will certainly cross that detection threshold. Okay? And this really just comes from looking at the bias in the drift of that mixture likelihood ratio.
This is for any h?
This is for any h that puts support on all theta. Yeah. So we use actually a mixing distribution that's a normal, so that's fine. But yeah, you have to be careful about that. Actually, it's quite interesting. In the literature on this, the h's that are considered usually have no mass at 0. So they actually have 0 density at 0. And that was one of the big differences in what we're doing. It's important to put a lot of mass at 0 because most effects observed in A/B tests are going to be around 0. OK. So it's guaranteed to detect any true effect eventually. And this is already pretty good, right? Because what this is telling you is that you've got a test which controls type 1 error and gives high detection. And in early versions of this work, this is kind of all we emphasized. But that's not good enough. What I want to do is now I want to use this and I want to think about how runtime and power are being traded off on shorter time intervals. So one thing I want to point out before we move forward is that if you use the always valid p-value process that comes from this S alpha, okay, which is basically stop. The p-value is the smallest alpha, such that the alpha level test would have rejected by now. Then actually that takes a very simple form for the mSPRT. It's just the infimum of 1 over the likelihood ratios up to this point. Okay? And that's really great, because this turns out to be computationally very simple. It can be done in browser for the client. So it's actually done on your web browser, as opposed to requiring kind of complex computation. One of the great things about that is that then it can be updated very, very quickly, and as people are reloading pages and so on. OK, so let me skip this. This is kind of the why it works, but I think I'd rather focus on some of the optimality results. So this is kind of what I was getting at. OK, so it has power 1 that's only asymptotically in the infinite data limit. And there's not really, it's not so much that that's in the infinite data limit that's the problem. It's that you're not getting a lot of resolution. There are a lot of tests of power 1, and one of our questions would be, is it actually trading off runtime and detection optimally, right? So how could we study that? It turns out to be kind of a delicate problem, and we want to be, you need to be a little careful how you define efficiency here. So what we want to do is we want to, I mean, and you could argue about this, we're all theorists, so arguably I'm going to define efficiency so I can prove something. But I like to think that the definition of efficiency is also kind of a reasonable one. So we show that the mSPRT trades off power and runtime efficiently, even when a user might abandon the test prematurely. So this is this user model I talked about, where the user is going to cut off the p-value at alpha if it ever falls below, but if it doesn't, they'll abandon for sure at m. They won't wait longer than that. OK, so this is probably the densest slide in the talk. So here's how I define efficiency. Given an m and an alpha, so that parameterizes the user. OK, m is how long they're willing to wait. Alpha is their type 1 error constraint. And an always valid p-value process, I'm going to think about two things. These exactly correspond to power and runtime. The first one is the expected runtime at a specific alternative theta. OK, so this is if the true value happened to be theta, they follow this decision rule, how long would the test run? And then the second one is the false negative probability, which is really 1 minus the detection. OK, so this is what is the chance that they failed to detect that there was a true effect despite the fact that there was one. And so this is what I just said. We're going to assume the user stops at the lesser of m or the first time the p-value drops below alpha. OK, so this is for our mSPRT with a particular user model. Now what I'm going to do is I'm going to compare that mSPRT to a different test which obeys the following two properties. Number one is that it also controls type 1 error. OK, so there's this hat test, which has a q hat and an r hat, that also controls type 1 error. And it has the property that its false negative probability is kind of 1 over 1 plus epsilon better than the false positive probability of our mSPRT, OK, overall theta. So basically, one way to think about this is think about the false positive probability as a profile over theta. Here's a test which is doing at least as good as ours and sometimes better. OK. So I'm giving it a band of 1 over 1 plus epsilon relative to our test to do better. Well, such a test has to inflate runtime. Okay? That's what I want. So what I want to be able to show is that for any such test, the runtimes of that test, the expected runtime of that test, has to be more than 1 plus epsilon times the expected runtime of our test. So informally, what's happening is that epsilon efficiency means that power can't be appreciably increased without significantly inflating runtime. Okay? And so what we do is our efficiency result basically considers performance of the mSPRT in the cheap data limit when m is large. So informally, I would state what we're trying to do here is show for users that have large m, we provide kind of an efficient trade-off between runtime and detection. Okay? And so how do we precisely state that result? Consider a sequence of users with a failure time that's going to infinity and alpha k going to 0. Now, why this? If alpha k doesn't go to 0, there's really no problem here, right? Basically, everyone is going to have perfect detection when alpha k doesn't go to 0, when mk goes to infinity. So this is kind of the right regime in which to study this trade-off. The mSPRT leads to epsilon efficient, always valid p-values for sufficiently large k, provided that this bound holds. And what this is saying is that the user should not be too conservative. So if alpha k is too small relative to their failure time, then no test can offer any detection, any appreciable detection. Okay? And so this is kind of the right scaling. This essentially says that this divided by mk has to be bounded. That's kind of the right scaling at which the user is actually getting detection. So this is fairly standard in the sequential testing literature as kind of a regime in which you would study performance. For us, what's interesting is that we're trying to deliver epsilon efficiency kind of for all sufficiently large k. The way I think about this is there's, most users of an A/B testing platform are running tests with thousands of observations. There's many visitors coming in. So that will fall well within the range of what one thinks of as large in a theorem like this. Okay? All right. So we interpret this result as follows. Users will have a range of risk preferences encapsulated through alpha and m. What we first do is control type 1 error for all of them. Right? And that was the kind of first part of the talk. That was always valid p-values. And this means that doesn't matter who you are, and actually not only for all of them, but actually any user model, type 1 error is controlled. Okay? Some users are going to be too conservative. Alpha will be too small relative to their m. And for them, power is going to be small under any method anyway. So we don't optimize for these users. For the remainder, alpha is quote unquote reasonable relative to m. And among those, we focus on those with larger m. Okay? And for those users, I would say the mSPRT achieves an approximately efficient trade-off between power and runtime uniformly over theta. That's kind of how I would talk about the previous result. So one point about this, anecdotally anyway, that I find really interesting is that I've always wondered, if I was going to kind of try to intuit what the trade-off between alpha and m is in practice, how would I recover that from what people in industry are doing? And one observation I would make, at Optimizely, there's a very wide range of customers, some who get millions of visitors into a test and some who get thousands. And so you can kind of see, what kinds of effects are they looking for, what are they able to detect, and so on. And you can talk to them as well. So one interesting thing, I think, is that in general, companies tend to be skating on exactly this boundary. And the reason is kind of obvious if you think about it. If alpha is too small, you're not going to detect anything anyway, so that's kind of not a useful exercise in experimentation. Also, if you're in a regime where, let's say, alpha is really large relative to your m, then you're going to get a lot of detections very, very quickly. Either those are all going to be correct, you got lucky, and despite the high false positive threshold, you ended up finding a lot of great things. Or you're going to be wrong and discover that a lot of that stuff was wasted time. Either way, you're going to rapidly find yourself into a regime where the stuff that you're testing are going to be progressively smaller and smaller effects. And so your alpha threshold is going to go down, your m is going to get larger. And so I think one of the interesting things I would love to maybe state a little more precisely is that my impression is that users find their way to exactly kind of the trade-off between alpha and m that we're talking about. I mean, it's sort of a natural thing that would happen if you imagine repeated experimentation in an environment where you could choose alpha and m freely. OK, so I have 2 more things I want to tell you. I've got, I think, 10 more minutes. Is that right? Yeah. Let me pause and ask if there's any questions so far. Yeah.
Did you consider some kind of cost-benefit model for this?
We did. Actually, the first model of this was a cost-benefit model. We essentially modeled things through an explicit cost to additional runtime, and then sort of view it as a standard decision theory problem. It's essentially equivalent to what we did here. I got to be honest with you that what I discovered was it was just harder to give that talk. So one of the reasons for that is slightly idiosyncratic, which is that the actual cost-benefit model that it corresponds to is one where the additional cost to observations is only in the H1 risk. So if you consider kind of what your cost looks like under null and alternative, you have a cost to error in the null, you have a cost to error in the alternative. It's only in the alternative that you add that additional cost on. And this is idiosyncratic for a couple of reasons. I mean, the obvious one is that, right, maybe the cost should be there for both. The reason it looks that way is because there is an asymmetry towards type 1 error. I mean, it's part of the reason we're controlling type 1 error first. And that asymmetry is that you default to preferring the existing outcome. So in some sense, there's no cost to observation there. So that's exactly what corresponds to the fact that we first control type 1 error and then optimize the other 2. I think you could do something similar by adding costs in both places, and it would be kind of a different approach from what I described here. Probably related, but I haven't thought that through. Yeah.
Do you ever think about what happens when m is, you can say that m is drawn from some sort of distribution, and then, you don't think about it as, does that make sense?
Yes, absolutely. It does make sense, yeah. So think about kind of average case robustness against the user. Yeah, we've talked about that as kind of follow-up to this, but we haven't really proven anything yet. I think in some sense, kind of what this is saying is think of distributions which put most of the mass out in the tail, and we're saying something about average case control in there. I think where it really gets interesting, obviously, is that you can see these distributions at Optimizely. That's why we got interested in it. But yeah, we haven't proven anything in that direction yet. That's a great kind of open question, I think. OK, so let me try to talk about the last 2 things quickly. So the first thing I want to talk about is, the first thing I want to talk about is something which is actually a quite important pragmatic concern. So the theory is all well and good. What this is basically showing is that essentially any mSPRT is kind of first order optimal in trading off runtime and detection. But you have to be wondering, that sort of feels a bit too slick, because that seems to completely ignore away effect sizes, right? So how could it be that you could pick any H you wanted? What if the mixing distribution puts very low weight on effects that I expect to see? That can't possibly be a good idea. So how do I capture that? Okay. So one way I could capture that is to actually do a bit more refined analysis of runtime, right? And so what we do is we say, OK, let's try to optimize runtime, but now under the assumption that the effect is drawn from a prior distribution. So this is kind of a Bayesian analysis of this algorithm. We're going to look at a prior G for the effect size and aim to minimize the expected run length. Remember, this R here is the expected run length, assuming that theta was the truth, for a user who has an m and an alpha. And now we're taking the expectation over that against a prior where theta comes from G. Okay? Now the question is, how should we choose the mixing distribution to optimize this run length among the class of mSPRTs? So this is kind of like second order optimality, I would say. So what we show, basically not surprisingly, is that the optimal choice of H depends on G. And in particular, the precise result is that we look at the limit where alpha goes to 0, and we show that the same limit that I had earlier, alpha going to 0, m going to infinity. And we show that the optimal choice of mixing distribution in the mSPRT involves roughly matching the mixing variance, which was sigma squared, to the prior variance, which was tau squared. Okay? And that's really nice, because we can measure a kind of a pseudo version of this prior variance by effect sizes that we see in the data. That's at least the approach we took. So what's nice about this is that if you look at what the matching looks like, the matching between prior variance and mixing variance, the constant of proportionality is actually something which is fairly robust across ranges of alpha and m. At least what we saw empirically is that if we end up let's say getting the constant the constant wrong by like a factor of say 10, we're still only like 5% off in expected runtime. Okay, so this is fairly insensitive. So this is actually a pretty nice thing, which is that we were able to find a way to actually specifically choose the mixing distribution inside the mSPRT to give good performance, on average across experiments that people would run. So this is exactly what's implemented in the Optimizely platform is a matching of the mixing variance to the prior variance. Okay. All right. So the last thing I want to talk about now is kind of, oh yeah, sorry. Got it. So do you mean, are you asking theoretically or practically? Yeah, so obviously we don't, the prior is not something that we have access to, but the way that we kind of construct a proxy for it from empirically observed effects. And by that I mean, actually, it's a good question. So let me maybe go into it for a minute. If you look at the tests that people run, there are many tests that people run longer than any point at which you would consider a reasonable detection threshold. And that's just because they were left running. They may have already determined the winner and just left the test running anyway. So what we did was that we analyzed sort of tests out to these longer run lengths to construct estimates of what we thought the prior distribution looks like. One of the nice things is that there's all kinds of fudging happening there. It's clear that this is not going to be a good estimate of the actual prior. But I think, again, it's not a claim I could theoretically prove, but the errors in that estimation are going to not affect the optimality properties here significantly because of the robustness property of this runtime minimization. OK, so last thing is then let me just turn back into the platform a little bit. And I guess what I wanted to do here was just say, if you had been a user, what would this mean to you? OK, so one thing you should understand, of course, is that if you have to give up something, right? I mean, there's no free lunch here. So if you had known the effect size in advance, then you should only be able to do better by doing something like what we're doing. And in fact, that's true. So when the effect size is known, you can use the standard SPRT of Wald. And of course, that's optimal in the strongest sense possible. It gives you minimum run length under both the alternative and the null. Okay? But the problem is that we don't know the effect size in advance, and the test we designed does not assume knowledge of the effect size in advance. It has this mixing distribution, but it doesn't assume you know exactly what the effect is. So I guess at some level, what I want to do is I want to ask, what's the effective uncertainty on the effect size? And that's the right place to do an apples-to-apples comparison to fixed horizon testing. What do we get when we compare? So this graph, let me interpret it for you. The x-axis is multiples. Okay. The y-axis is it's a histogram of over many experiments. I think there were 40,000 experiments that we looked at here. These were all experiments of the sort in my answer to Kamish, where they ran for a very long time relative to whatever would have been a reasonable detection time. So you can think of it as having like free data on which to simulate whatever testing approach you wanted. So on those tests, what we did first is we said, OK, let's treat the final observed effect size as the true effect. And for that, compute the optimal sample size and run the fixed horizon test and compare it to what we do. Right? And in our case, what we get that's the solid black line. Sorry, no, that's the dotted line. What you find is that often we will inflate run lengths significantly by a factor of 2 or even 3. Okay? Now, why is that happening? That's because if you happen to know the exact effect size, then the fixed horizon test actually picks a pretty good sample size. Okay? And in this case, we're picking heavily inflated run lengths. But now suppose that instead what I do is I imagine that when I picked out my sample size for the fixed horizon test, I did so under the assumption that the effect was actually going to be smaller than it really ended up being. Okay? Maybe I was off by 30% or 50%. This isn't unreasonable in practice, okay? Where like if you look at some of these tests, the conversion rate might have been 10% at baseline. You're looking for a 0.5% effect. Now 0.5%, it's easy to imagine that in fact you're going to be looking for like 0.3 or 0.7 or something, 0.03 or 0.07. So I think it's like, no, I got that right the first time. So it's the kind of thing where you can easily be off by 30 or 50% in that estimation of the actual effect. Now, if you are off by that much, notice what happens. The run length under our test suddenly starts becoming much better relative to the fixed horizon test. Okay? And what's happening there is that if you were uncertain about the effect size, the fixed horizon test is actually quite conservative. Detecting an effect of size delta takes a run length proportional to 1 over delta squared. That's pretty standard. And so the penalty for guessing wrong about delta is very high. If you happen to pick your MDE 2x too small, you're going to end up with a run length that's 4x too long, okay, in the fixed horizon test. Whereas the continuous test, continuous monitoring test will adjust for that. And so the way we kind of show this theoretically is we say, OK, let's look at a regime, again, the same kind of regime where alpha goes to 0 and n goes to infinity. What we show is if you truncate a test at theta n, so you give us the same number of samples as a fixed horizon test, we can, wait, sorry. Sorry, yeah. So look at an mSPRT that's truncated with a maximum failure time, which is order of the fixed horizon test. We get the same power as the fixed horizon test at a detection time that's little o of n. Okay? So that user model where he stops at a failure time or the first time the p-value drops below alpha, that person is going to stop in sort of time that's little o of the fixed horizon run length in a world in which the effect size is unknown in advance. Okay, so from our perspective, what this meant was even if you were a great user of the previous Optimizely dashboard, okay, the fact that effect sizes are unknown mean that you're still probably going to be better off using detection from this approach. Yeah.
Does appropriate scaling regime just mean that alpha goes to 0 slower than?
Yeah. So basically, I'm not spelling this out. It's that same kind of.
Convergence rate to 0.
It's the same kind of scaling that I talked about earlier. This like log 1 over alpha over n. It's like log 1 over alpha needs to be little o, big O of n. OK. Sorry, I'm rushing a bit. I'm just running out of time. So I won't say much about this. Like I said, I think the main point I would make here is that there are a variety of different approaches to controlling for multiple hypothesis testing. I showed you the dashboard, actually. That dashboard, it's amazing. You'll find it in every company where there's this kind of matrix of greens and reds. Everybody that runs A/B tests has dashboards that look like that. It'll be very standard to have maybe 30 to 50 cells in that dashboard. So you've got a multiple hypothesis testing problem with 50 hypotheses. A lot of the nice thing about the Optimizely dashboard is because we're generating a different calculation for p-values, we can combine that with multiple testing corrections that are fairly standard. And so some of the theory in the paper is just to make sure that those corrections commute in the proper way. So I won't talk about that. All right, so let me wrap up. I guess one of the things I want to emphasize from this work, just zooming out a little bit, what I found really exciting about it and kind of the types of problems that have got me motivated moving forward is this idea of introducing the user as a third party into the analysis. I think there's just a lot of interesting questions that pop up there. It might appeal to me because I come from a more mechanism design background, and so I'm accustomed to thinking about sort of designing against users in a platform. And I think what's nice about this is that the class of problems where you think of a user as having an objective function, and now you're delivering sort of statistical output to them to achieve kind of a desired optimal outcome jointly, I think that's actually vast, right? That'll apply even for many of these kind of bandit algorithms where people are intervening in successive application of the bandit. And so, so I think like what I would love to be able to do is sort of more work of this sort where you're adapting statistical methodology to act in partnership with the user. As I mentioned, there are additional results. All of this stuff kind of goes through with confidence intervals. There's an exact duality between p-values and confidence intervals. And then we have some initial results on applying these always valid p-values to actually get p-values and confidence intervals for multi-arm bandits. So I'm happy to talk about that offline if you'd like. OK, and I guess the last point is just this was launched on January 20th, 2015. And as I said, in the dashboard, they provide always valid p-values and the multiple testing corrections. Thank you.
Maybe
couple of questions.
So with this thing, can you now say how much longer do you need to run?
Yeah, actually, so I haven't checked exactly what the current design of that same page is like, but now, yes, now we can. So in a sequential testing setting, we can make statements about expected runtime. Again, we have to do that with respect to an assumption about how the user will behave. So the specific assumption we're making is, the specific thing we're trying to calculate is the expected time until the test will terminate under some guess about what we think the effect size is actually going to look like. So
Give him some information about it.
yeah, that's right. So now, though, it's actually meaningful. And in particular, the most important thing is biasing their decision on the basis of the display of that information is fine, because it's, they're allowed to make data-dependent decisions.
Before we take the next question, if there are any, we need to change speakers. So
Oh, sure, yeah.
Change at the same time.
Here you go, Emily.
Ramesh can multitask.
Oh, you have yours. OK. Great. Yep. I think.
Any other questions for Ramesh?
Perfect. OK, good. Thank you. Oh, wait, was there another question? Oh, OK. Sorry, Ramesh.